Hello, welcome to the course on emerging domain electronics engineering. This is lecture 25, and in the previous lecture we have seen what is modulation. So now in this lecture we will see what is the need of modulation, why the modulation is required in a communication system. So as per the definition of modulation, it is a process in which the parameters corresponding to the carrier wave is varied in accordance with the instantaneous value of massive signal, that is called the modulation, and we have seen the continuous wave modulation as well as pulse modulation. So now what is the need of modulation? Since the baseband signal or the massive signal is not compatible for the direct transmission over the channel. So for these massive signals or the baseband signals to travel long distances, so its strength has to be increased. If we increase the strength with the help of the modulation process by, or we can say with the help of high frequency carrier wave or with the high frequency carrier signal, so it basically does not affect the parameters of the modulating signal, or which is called as the massive signal. So this is the need of modulation, means if we want to transmit the massive signal or the baseband signal for the longer distances, or we want to increase the strength of the signal so that it can reaches a very large distance, so we need the modulation. So after that we have with the help of this modulation we have the reduction in the size of antenna. We will see that modulation, it avoids intermixing of signals. With the help of this modulation, the range of the communication system, we can increase the range also. It allows multiplexing. Multiplexing means we are transmitting more than two signals simultaneously, so that is called as multiplexing. After that we will see, with the help of this modulation process we improve the quality of reception. So in this need of modulation, first we will start with the reduction in the antenna size. So for the effective transmission of signals, the height of antenna required is in terms of lambda, means in terms of wavelength, and at least the height of antenna must be lambda by 4. So we can say that height of antenna is related to a parameter which is wavelength, and it must be h is somewhat lambda by 4. So if we are considering the low frequency massive signal, means the signal having a low frequency, that means correspondingly their wavelength is very high, and if the wavelength is very high, and if we compute, let us say what is the length of the antenna required at 10 kilohertz, then what happen? The minimum height of antenna is lambda by 4, and we are aware that lambda equals to c by f. So if we will put here, then the height of antenna comes around 7500 meter, which is somewhat 7.5 kilometers, means this much high, this much height is required for the antenna, 7.5 kilometers, which is very high. And if we will see that if we are transmitting signal at 10 megahertz, then the height of antenna required with the help of this relationship is around 75 meter. So if we will see that if we will perform transmission at low frequency and high frequency, what is the difference? At high frequencies we can say the height of antenna requirement is low, means not much. We will compare that 7.5 kilometer and 75 meter, then we are able to understand that 75 meter is very small in comparison with 7.5 kilometer, which is practically feasible to design also. So it will decrease the design cost of antenna, and it basically we can say the cost also reduced. So we can say that the modulation is required for the massive signal, and with the help of modulation we will convert our baseband signal, which is a low frequency signal, into a higher frequency signal, and finally which is having a solution, the practical value for the height of antenna. So we can achieve the practical height of antenna at high frequency. After that avoid mixing of signal, or we can say it is the intermixing of signals. So, what happen is, if we are transmitting the baseband signal without using modulation, then what happen? Then these signals will be mixed. Let us say we will take an example that we have 3 voice signals and we are transmitting, let us say this is x1, x2 and x3, and if we are transmitting through a channel, and since it is a voice signal, so the frequency is 20 kilohertz for all these 3 signals x1, x2, x3. So, if you are transmitting directly over the channel, what happen is there will be mixing at the receiver side, there will be mixing of these signals x1, x2, x3. But let us say if we are modulating these 3 baseband signal at some different carrier, so what will happen, that if we are modulating, let us say this signal at, let us say 100, or let us say this is at 200, this is at 300, then we will have something like this: first peak, second and third, like this. This is our x1, this is x2, this is x3. We will see in our next slide that how this frequency translation is achieved using modulation. So, here we can clearly see that these frequencies are different, and if we are transmitting through the channel, so the information will not be mixed. So, means here we have concluded that with the help of modulation, the intermixing can be avoided, and after that the increase the range of communication. So, what happen is, the frequency of the baseband signal is low, as we are already aware of the fact. So, these low frequency signals will not be able to travel long distance. So, as a result, we must perform some these signal will not travel for long distances, and they will get highly attenuated. So, this attenuation basically reduces the increase in the frequency of transmission signals. So, we can say that with the help of this modulation process, we increase the frequency of the signal which is to be transmitted. Therefore, it increases the range of communication, and with the help of this, if we increase the frequency, then the attenuation, the level of attenuation is also low. So, this is the increase the range of communication. After that, we have the allow multiplexing of signals. As we have seen in our last slides that with the help of modulation, the intermixing can be avoided. So, what is multiplexing here? Multiplexing is basically a process in which 2 or more signals can be transmitted over the same communication channel simultaneously. Means we do not need separate channels for individual signal. We have a single channel, but we have so many message signals, and we are transmitting these message signals simultaneously over the channel. That is called as multiplexing. So, this multiplexing is possible only with the help of the modulation. So, here we can see that this multiplexing basically allows the same channel to be used for many signals. So, hence in a TV channels can be used as the same frequency range without getting mixed with each other, or different frequency signal can be transmitted at the same time. So, we have the multiplexing techniques, time division multiplexing, we have the frequency division multiplexing. So, here is that we are transmitting messages simultaneously over a same channel, that is called as a multiplexing. So, after this, improves quality of reception. So, it has been observed that in the frequency modulation, which utilizes the digital communication techniques, which is pulse code modulation PCM, the effect of noise is reduced. The noise effect is reduced to a greater extent. So, basically if the noise content or if the noise is reduced, then we can say that quality of reception improves. Then the quality of signals which are received at the receiver side, they get improved. So, this is again the this is the fifth point, improves the quality of reception. So, after this need of modulation, if you will see, if we have already visualized that what is the chart for the modulation. So, in the continuous wave modulation we have the amplitude modulation and angle modulation. Similarly, we have the pulse modulation techniques in digital also and in the analog also. So, now we will start with the amplitude modulation. So, first, what is amplitude modulation? So, in general we have seen that what is modulation. So, what is amplitude modulation? In amplitude modulation, the amplitude of high frequency carrier wave is varied in accordance with instantaneous value of massive signal or baseband signal, keeping frequency and phase constant. So, this kind of technique, this kind of modulation is known as amplitude modulation. So, let us see here, a continuous wave goes on continuously without any interval and it is the baseband massive signal, which is the low frequency, which contains the information. So, this message has to be modulated, or this information has to be modulated, because we have seen that with the help of modulation, what is the advantage? What is the advantage of modulation? We have seen. So, according to this definition, the amplitude of the carrier signal is varied in accordance with the instantaneous value of the modulating signal, keeping phase and frequency constant. So, which means that the amplitude of the carrier signal contains no information. Basically, this carrier name, the carriers basically is used to basically travel the massive signal to the long distances. It helps basically in reaching the signal, in basically transmitting the signal to the long distances. So, after this, how we can achieve the waveform? This is the waveform for the amplitude modulation. Let us see, this first is the massive signal. Let us say this is MT is AM cos omega MT. Similarly, this is carrier signal, CT equals to AC cos omega CT. Now, as per the definition of this amplitude modulation, what we say that, let us say this is ST is nothing but A cos omega CT. This is, let us say, first equation, this is, let us say, second equation, this is third, where A is nothing but AC plus AM cos omega MT. So, if we are utilizing these first, second and fourth equation, and will substitute in equation number 3, then we can achieve that ST is nothing but AC plus AM cos omega MT and finally cos omega CT. This is the equation of AM. So, here how this waveform for AM is plotted, we can see. First of all, we must observe that omega C is very high in comparison with omega M, as per the definition of modulation, that high frequency carrier, that means carrier frequency is very high, that means this waveform is somewhat compressed. After that, we can say that cos omega MT means, depending upon this cos omega MT can be +1 or -1. Similarly, this is cos omega CT, it can be again +1 or -1. So, when omega M, this factor is, let us say, +1, then we achieve AC plus AM cos omega CT, and when this factor is negative, then we have AC minus AM cos omega CT. Now, depending upon the value of cos omega CT, we have either positive or negative, means either positive this way or this way. So, from these two equations we can achieve 4 factors. First is AC plus AM, second factor will achieve minus of AC plus AM, and from the second one we achieve AC minus AM and negative of AC minus AM, like this. So, in this particular region, if we will talk about for this particular region, we can observe that no signal is present, no message. So, when there is no message, then what we can say that then the waveform here we achieve only the carrier, something like this. We achieve only the carrier. After that, what happened at this particular point where this is maximum, then we achieve the maximum value which is AC plus AM. After that, we achieve this value which is AC minus AM, and similarly this will be minus of AC plus AM and minus of AC minus AM. So, these are called as the envelopes. These are called as the envelopes. So, basically we have this kind of waveform for the amplitude modulation, like this, where it is having two envelopes, which is this is the upper envelope, this is the lower envelope. So, this AM basically contains the carrier as well as the message signal. So, this is the waveform, this is the time domain representation for the AM signals. Now, as we have seen that we have the message signal, we have the carrier CT, and we have the equation of AM. So, in the last slide we have seen this is the relationship, and the final waveform, final equation in time domain for AM signal is ST equal to AC plus AM cos omega MT and cos omega CT. So, this is a small derivation how we can derive the equation of AM signals. Now, we will utilize this particular equation to calculate a very important factor which is called as the modulation index. So, first, what is modulation index? So, basically a carrier wave after being modulated. So, if the modulation level or if the modulated level is calculated, then this type of attempt is known as the modulation index, or somewhere referred as the depth of modulation. It basically states the level of modulation that a carrier wave undergoes. Means what is the level of modulation? We will see, we will define that under modulation, over modulation, critical modulation we will define. So, if we will take AC common from our last equation, then we have this equation AC 1 plus AM by AC cos 2 pi FMT and cos 2 pi FCT. Now, this factor AM by AC is if we define by mu equals to AM by AC, this is called as the modulation index or the depth of modulation. So, we have seen where AM is the amplitude of message signal, AC is the maximum amplitude of carrier signal. So, we are going to utilize now this particular equation which says ST equal to AC 1 plus mu cos 2 pi FMT and cos 2 pi FCT. So, now we will use this equation for basically calculation of the modulation index. How we can calculate modulation index from the waveform. So, as we have seen that in our envelope, if we have if we will see this kind of envelope in AM like this and so on. So, we have seen that this value is AC plus AM, the maximum amplitude is AC plus AM and the minimum was AC minus AM. A min equals to AC minus of AM. So, if we are basically adding these two equations, then we achieve that AC equal to A max plus A min by 2, means the maximum amplitude plus the minimum amplitude divided by 2. After that, if we will subtract these two equations, this one and this one, then we achieve that AM equals to A max minus A min by 2. So, if we will put these two values of AC and AM in the modulation index, which is mu equals to AM by AC here, then we have mu equals to A max minus A min divided by A max plus A min, means with the help of this particular envelopes, which is called the A max and this is called the A min. So, this is basically the A max minus A min divided by A max plus A min will give you the value of modulation index, or what is the depth of modulation. So, on this basis of this depth of modulation, we will have, let us say, 3 cases. First is, let us say mu equals to AM by AC, and we just say that mu is between 0 and 1. Mu is between 0 and 1. Let us say for this particular case, which says that 50% modulation, that means 1 by 2, mu equals to half, mu equals to half, which is nothing but 50%. So, what happen is, if mu is less than 1, then we can clearly see here, and this will be AC is, this says AC is greater than AM, means the amplitude of carrier signal is greater than that of the message signal. So, what happen is, we can see these envelopes. This is AC plus AM and this one was AC minus AM. But now we will see here what happened when mu equals to 1. When mu equals to 1, it says that AC equal to AM. AC equal to AM, if we will put here, then we will achieve double, 2 times of AM, and this will be 0. So, what happen is, both the envelopes basically touches at a particular point, means at this particular point, and this is known as the critical modulation. Critical modulation. Now, when mu is greater than 1, means AM by AC, this is greater than 1. So, AM is greater than AC. What happen is, AM greater than AC, if we will put here, then we have the positive value, but here AC minus AM and AM is greater than AC, then what happen is, this envelope will go in this particular direction, it will become negative, and here it will become positive. So, what happen is, in this particular region there is a mixing of envelopes. So, at the reception, at the receiving side, we cannot basically detect these envelopes because they got mixed, intermixing. So, this is over modulation, this is called as the over modulation, which is avoided. So, basically we just prefer this particular, that mu is somewhat between 0 and 1. Now, the bandwidth is a range of frequencies. Range means F max minus F min, this is a range of frequencies. So, if we will expand the equation of AM, then we will achieve, let us say, 3 factors. One is totally the carrier, second contains the FC plus AM, FC plus FM, and this third factor contains FC minus FM. So, this is called as the upper sideband USB, this is called as the lower sideband, whereas this is called as the carrier, this is the carrier itself. So, the amplitude of upper sideband and the lower sideband is mu AC by 2, and the frequency of the upper sideband is FC plus FM, whereas for lower sideband is FC minus FM. So, if we will visualize here, then what we will have, will have, let us say, if we will draw something like this, this is Fc plus Fm and this is Fc minus Fm. So, this is the bandwidth, this is the range of frequencies. So, it comes around 2 times of Fm. So, bandwidth of AM signal is 2 times of Fm. Now, the power calculation. So, the power calculation, it says that if it is having 3 factors and we can individually calculate the power of the individual waveform, means first we will calculate the power of carrier, after that for upper sideband, after that for lower sideband, and we will club all these powers. So, for this particular signal AC cos 2 pi FCT, we must aware that in signal system we have seen that how we can calculate the power of a sinusoidal signal. So, the power is nothing but A square by, we have basically A square by 2. So, we can see that PC and PUSB and PLSB, and power is something like this, Vrms square by R, and Vrms is, we are aware that it is Vm by root 2 whole square divided by R basically, this is R. So, now what happen is, first is the carrier power. So, the amplitude of the carrier is AC. So, AC by root 2 and which is AC square by 2R. For upper sideband we have basically mu AC by 2. So, this is square and we must take the RMS. So, this is square by R, which is something AC square mu square by 8R, and finally for LSB the value is also same. So, what happen is, if we will club these all the 3 terms, or we can clearly see that the carrier power is, if we will normalize this, then resistance will, let us say, equals to 1. So, it is AC square by 2, this one was AC square mu square by 8, and this is something AC square mu square by 8. So, now we are clubbing these all the 3 terms because we are interested in calculating the total power, total transmitted power of the AM signal. So, PT equals to PC 1 plus m square by 2, 1 plus mu square by 2. This is the most important relationship, where PC is corresponding to the carrier power and PC mu square by 2 is total sideband power. Total sideband power. So, if the value of modulation index at critical modulation mu equals to 1, then what happen is mu equals to 1, it is 1.5 times the carrier power. So, the power required for the transmission of an AM wave is 1.5 times the carrier power for a perfect modulation. We cannot increase the value of modulation index beyond 1, because the signal will, the envelope will be mixed and we cannot recover our information back. So, now we have the current relationship of AM. Current relationships, as we have seen the relationship for power, PT equals to PC 1 plus mu square by 2. So, if we will have PT by PC, we will have something like this, and PT is, let us say, I square R. So, instead of PT, if we will normalize this relationship, then PT is nothing but IT square. So, we will put directly IT square over here, IC square over here. So, this give us a relationship between the total transmitted current in terms of the carrier current, IT equal to IC under root of 1 plus mu square by 2. Now, we have one last case which is called as a simultaneous modulation, means when the signals are simultaneously modulated using AM, then what is the effective modulation index? The effective modulation index we can calculate as mu equals to mu 1 square plus mu 2 square plus mu 3 square, and finally we have the under root. So, with the help of this we can basically calculate the overall modulation index, and after that we can utilize this overall modulation index in this relationship or in the calculation of the total transmitted power. So basically we have seen, if we will summarize that, we have seen for AM the amplitude of upper sideband and lower sideband, that one was mu AC by 2. After that we have seen the frequency of upper sideband, which is Fc plus Fm. For lower sideband it was Fc minus Fm. Bandwidth we have seen, bandwidth is let us say 2 times of Fm. We have seen the total transmitted power, which is Pt equal to Pc 1 plus mu square by 2, and we have seen the relationship for current also. So these formulas basically helps in calculating the values, the bandwidth, the upper sideband, lower sideband frequencies, the amplitude of the upper sideband, lower sideband, what we called as the current, and we can see the situations of the simultaneous modulation also. So these are the references. Thank you.